Good evening and welcome to Physic for Sleep. Tonight we embark on an intellectual journey exploring the enigmatic realm of antimatter, the mirror reflection of our world, and the profound mystery of where it might have gone. Before we gently immerse ourselves in the profound implications of antimatter, I would like to know where you are at this moment. Perhaps you're gazing out a window at the quiet city lights, reflecting on the day's events. Or maybe you're nestled under a warm blanket, listening to the gentle rhythm of the night. If these deep reflections help you relax and organize your thoughts before sleep, please support the channel with a like and subscribe so others can find their way here too. Now, just breathe, allow your eyes to grow heavy, and let's begin. The concept of antimatter might, at first glance, seem like something reserved for the pages of science fiction, a fantastical counterpart to our familiar reality. Yet, within the rigorous framework of physics, antimatter is not merely a hypothetical construct. It is a fundamental aspect of our universe, a profound mirror reflection of every particle that makes up our world. Imagine, if you will, that for every electron, every proton, every neutron that forms the atoms around us, there exists an almost identical twin. This twin shares the same mass, the same spin, the same fundamental properties, but carries an opposite electrical charge and other reversed quantum numbers. These quantum numbers, subtle descriptors of a particle's intrinsic nature, such as lepton number or baryon number, are inverted for antiparticles, creating a perfect yet opposite counterpart. So, an electron, with its negative charge, has an antiparticle known as a positron, which possesses a positive charge. Similarly, a proton with its positive charge has an antiproton, which carries a negative charge. Neutrons, being electrically neutral, have antineutrons, which, while also neutral, have their constituent quarks and antiquarks arranged in an inverse configuration. This elegant symmetry, discovered not through direct observation initially, but through the profound depths of theoretical mathematics, speaks to a deeper order within the cosmos. The intellectual journey to antimatter began in the late 1920s with the brilliant work of the British physicist Paul Dirac. He was attempting to reconcile the seemingly disparate theories of quantum mechanics, governing the very small with Albert Einstein's special theory of relativity, describing objects at high speeds. His groundbreaking equation, published in 1928, aimed to describe electrons moving at relativistic speeds, demanding mathematical elegance. What emerged from his framework was startling. The equation yielded not just one solution for the electron, but two. One described the electron as we knew it, with its negative charge and specific energy. The other predicted a particle with the same mass as the electron, but with a positive charge. Initially, Dirac himself was hesitant, wondering if this second solution might represent the proton, a known positively charged particle. But the mathematics insisted on a particle with the electron's mass, not the proton's much greater mass. It was a bold prediction, one that seemed almost too perfectly symmetrical to be true, yet the beauty of the equations compelled him to publish. Just 4 years later, in 1932, during cosmic ray experiments high above Earth, American physicist Carl Anderson observed a particle that left a track identical to an electron's in a cloud chamber, but curved in the opposite direction when subjected to a magnetic field. This distinct curvature clearly indicated a positive charge. He named it the positron, a portmanteau of positive electron, confirming Dirac's astonishing prediction and forever altering our understanding of matter. This discovery was a landmark, validating a purely theoretical concept and opening up an entirely new dimension of particle physics. It showed us that the universe is not just composed of matter, but also of its spectral opposite, antimatter. The implications of this duality are immense, suggesting a fundamental balance, or perhaps an imbalance, at the heart of existence itself. The most striking characteristic of antimatter, and perhaps the one that truly defines its nature, is its interaction with ordinary matter. When a particle of matter encounters its antiparticle counterpart, they do not simply bounce off each other or pass by. Instead, they mutually annihilate in a burst of pure energy. This is not a violent explosion in the dramatic sense, but rather a profound transformation, a pristine conversion of mass directly into energy, following Einstein's iconic equation, E equals mc squared. For instance, when an electron meets a positron, their combined mass is entirely converted into photons, typically 2 gamma rays, traveling in opposite directions. To put this into perspective, even a tiny amount of matter and antimatter, say a single gram of each, would release an amount of energy equivalent to a significant nuclear weapon, but in a far cleaner, more direct fashion. It is a fundamental process, a kind of cosmic reset button, where the very substance of existence can dissolve into light. This annihilation process is not merely a theoretical curiosity, it is a measurable phenomenon with practical applications that touch our lives even now. In medical imaging, for example, positron emission tomography, or PET scans, utilize this very principle. A radioactive tracer that emits positrons is introduced into the body. These positrons then travel a short distance, typically less than a millimeter, encounter electrons, and annihilate, producing pairs of gamma rays that shoot off in exactly opposite directions. By detecting these coincident gamma rays, doctors can precisely map metabolic activity within tissues, providing invaluable diagnostic information for diseases like cancer or neurological disorders. This quiet, invisible dance of creation and annihilation is happening within our own bodies, revealing the subtle workings of life itself, a testament to physics on the smallest scales impacting our well-being. The existence of antimatter compels us to ponder the deep symmetries of the universe. If for every particle there is an antiparticle, then it seems logical to assume that at the moment of the Big Bang, when the universe burst into being from an unimaginably hot and dense state, equal amounts of matter and antimatter should have been created. This is a principle of fundamental physics, known as charge parity or CP symmetry, which posits that the laws of physics should remain the same if a particle is swapped with its antiparticle and its spatial coordinates are inverted. If this symmetry were perfectly upheld in the early universe, energy would convert into particle-antiparticle pairs in equal measure. Yet, when we observe our universe today, we see an overwhelming abundance of matter. Galaxies, stars, planets, and indeed ourselves are all made almost exclusively of matter. Where, then, did all the antimatter go? This cosmic asymmetry, this apparent deficit of antimatter, is one of the most significant unsolved mysteries in modern physics. It is the central puzzle that guides our exploration tonight. Consider the profound implications of this cosmic imbalance. If there were truly equal amounts of matter and antimatter in the early universe, they would have annihilated each other completely as the universe cooled, leaving behind only a sea of photons, a universe devoid of stars, planets, or life, a silent expanse of pure radiation. The very existence of our world, and our presence within it, is a testament to some subtle yet crucial deviation from this perfect symmetry. Scientists are actively searching for the mechanisms that could have led to this matter. Antimatter asymmetry, a process often referred to as baryogenesis. The question of how our universe came to be dominated by matter, despite the expectation of perfect symmetry, leads us into one of the deepest conundrums of cosmology. To understand how such an imbalance could arise, we turn to the visionary work of the Soviet physicist Andrei Sakharov. In 1967, Sakharov proposed 3 essential conditions that must be met for a universe, starting with equal amounts of matter and antimatter, to evolve into one that is predominantly matter. These conditions are like the ingredients in a cosmic recipe, each vital for the ultimate outcome. First, there must be a process that violates baryon number conservation. Baryon number is a quantum number assigned to particles like protons and neutrons, collectively known as baryons, and their antiparticles. In simple terms, this means that processes must exist where the total number of baryons minus antibaryons is not conserved. This would allow for the creation of more baryons than antibaryons. Second, there must be C and CP violation. C stands for charge conjugation, which means if you swap a particle with its antiparticle. CP stands for charge parity, meaning the laws should be the same and also reflect its spatial coordinates, like looking in a mirror. If these symmetries were perfectly preserved, matter and antimatter would behave identically, leading to no net excess of matter. The universe would be perfectly balanced and perfectly empty. Third, these processes must occur out of thermal equilibrium. This implies a period in the early universe where the rate of interactions creating matter-antimatter pairs was not balanced by the rate of their annihilation. Imagine a cosmic dance where the partners are constantly forming and dissolving. If the dance happens too slowly, or if there's a moment when one type of dancer is slightly favored, that subtle advantage can be amplified, leading to a lasting asymmetry. Among Sakharov's conditions, CP violation is perhaps the most intriguing, as it directly addresses the subtle differences in behavior between particles and their antiparticles. Imagine two dancers, perfectly choreographed, moving in a grand cosmic ballet. If CP symmetry holds, then if you were to replace one dancer with their mirror image and the other with its antimatter mirror image, their dance would appear exactly the same. But if CP is violated, then the mirror image dance would subtly differ from the original. In the realm of particles, this means that certain decay processes might occur at slightly different rates for particles compared to their antiparticles, or produce different distributions of daughter particles. This tiny, almost imperceptible bias, if present in the incredibly hot and dense early universe, could have led to a minute excess of matter over antimatter. Experimental evidence for CP violation has indeed been found, most notably in the 1960s with neutral kaons, and later, more significantly, with B mesons at particle accelerators such as BABAR and BELLE. These experiments observed that kaons and B mesons decay into their respective products at slightly different rates than their antiparticle counterparts. This tiny asymmetry, perhaps 1 part in a billion, is precisely the kind of subtle deviation from symmetry that Sakharov's conditions required. While the CP violation observed in these experiments is not large enough to explain the entire matter-antimatter asymmetry of our universe, it demonstrates that such a fundamental process is indeed possible and active within the standard model of particle physics. It hints at a deeper, more profound CP violation that might have occurred in the very first moments of cosmic history. The search for the full explanation of baryogenesis, this cosmic generation of baryons, continues to be a frontier of theoretical physics. One leading candidate involves a hypothetical process known as leptogenesis, which postulates that a slight asymmetry in the production or decay of heavy, unstable neutrinos, the ghostly, nearly massless particles, could have generated a lepton asymmetry. This lepton asymmetry could then have been converted into a baryon asymmetry through other processes, such as those occurring within the Standard Model during the electroweak epoch, a period when the electromagnetic and weak forces were unified. Another theoretical avenue explores mechanisms tied to the dynamics of the Higgs field, the omnipresent field responsible for giving particles their mass. During a phase transition in the early universe, as the Higgs field settled into its current state, it is conceivable that conditions arose that favored the creation of matter over antimatter. These grander theories, often extending beyond the Standard Model, attempt to paint a more complete picture of the very earliest moments of our universe, moments when the fundamental constants and forces were still finding their ultimate form. While these theories offer compelling possibilities, the ultimate experimental verification remains elusive. Scientists are continuously pushing the boundaries of technology to search for primordial antimatter in the cosmos. The Alpha Magnetic Spectrometer, or AMS-02, an instrument aboard the International Space Station, is meticulously scanning cosmic rays for any signature of antinuclei, such as antihelium. The detection of even a single antihelium nucleus would be a monumental discovery, hinting at the existence of distant regions of the universe dominated by antimatter. So far, AMS-02 has detected millions of helium nuclei, but no antihelium, reinforcing the picture of a matter-dominated local universe. This absence, however, doesn't entirely rule out antimatter in far-off galaxies. It simply means that if such antimatter galaxies exist, they are likely separated from our own by vast empty voids, or perhaps even by cosmic barriers that prevent matter-antimatter annihilation at their boundaries. On Earth, physicists are not just searching for antimatter, but actively creating and studying it in laboratories. At CERN, the European Organization for Nuclear Research, scientists produce antiprotons and positrons to form antihydrogen atoms. These delicate antimatter atoms are then trapped and cooled, allowing for precise measurements of their properties. The goal is to compare antihydrogen with ordinary hydrogen to see if there are any subtle differences, any violations of CPT symmetry. CPT symmetry, a more encompassing principle than CP symmetry, states that the laws of physics should be invariant under simultaneous transformations of charge conjugation, parity, and time reversal. According to our current understanding, CPT symmetry must be perfectly preserved. Any deviation, however minuscule, would send ripples through our entire understanding of the universe. So far, within the limits of experimental precision, antihydrogen appears to be an exact mirror image of hydrogen, confirming the elegance of this fundamental symmetry. The sheer scale of the problem of matter-antimatter asymmetry is humbling. For every billion pairs of matter and antimatter particles that annihilated in the early universe, there was just one extra matter particle left over. It is this tiny, almost insignificant residue, this cosmic 1 in a billion surplus, that eventually coalesced to form all the galaxies, stars, planets, and ultimately us. We are, in a very real sense, a cosmic accident, a consequence of a fundamental imbalance that allowed structure to emerge from the fiery crucible of the Big Bang. When we gaze at the tranquil night sky, each star, each distant galaxy, is a luminous monument to this subtle asymmetry, a reminder that our existence is woven into the very fabric of the universe's fundamental laws, or perhaps its exquisite exceptions. The precise confirmation of CPT symmetry through experiments like those at CERN, where antihydrogen behaves indistinguishably from hydrogen, underscores a profound truth. The laws of physics are indeed symmetrical when charge, parity, and time are simultaneously reversed. This means that antimatter is not merely an opposite substance, but a perfect reflection, a precise mirror image of matter. Therefore, the cosmic imbalance cannot stem from any inherent static difference between matter and antimatter themselves. Instead, the asymmetry must arise from dynamic processes, from conditions in the very early universe where these symmetries were subtly broken in a fleeting yet decisive manner. This realization pushes us beyond the familiar confines of the standard model of particle physics, which, while incredibly successful, does not contain sufficient sources of CP violation or baryon number violation to explain the observed dominance of matter. To unravel this cosmic riddle, physicists are exploring theories that venture beyond the standard model. One prominent avenue involves what are known as Grand Unified Theories, or GUTS. These theories propose that at incredibly high energies, far beyond what our most powerful accelerators can achieve, the strong, weak, and electromagnetic forces, which appear distinct in our everyday world, were once unified into a single, overarching force. Within the framework of many GUTS, new super-heavy particles are predicted to exist, particles that could mediate interactions capable of violating baryon number conservation. Such interactions would allow protons, for instance, to decay into lighter particles, a process that has never been observed but is actively sought in large underground detectors. If these hypothetical GUT particles were abundant in the extremely hot early universe and decayed with a slight preference for matter over antimatter, they could have generated the initial imbalance required by Sakharov's conditions. This scenario paints a picture of a primordial soup, where exotic particles briefly existed, leaving behind a subtle yet universe-defining residue of matter. Another elegant solution to the baryogenesis puzzle, one that has gained considerable traction, is known as leptogenesis. This theory focuses on the enigmatic neutrino, a particle so ethereal it can pass through entire planets without interaction. While the Standard Model describes neutrinos as massless, we know from neutrino oscillation experiments that they do possess tiny masses, implying physics beyond the Standard Model. Leptogenesis posits the existence of incredibly heavy, sterile neutrinos, which are not predicted by the Standard Model. These hypothetical heavy neutrinos, if they existed in the early universe, could have decayed asymmetrically into leptons and antileptons. This initial asymmetry in leptons, such as electrons and neutrinos, a process called electroweak Sphaleron transitions. These transitions, occurring when the universe was extremely hot, are non-perturbative processes within the Standard Model that can change lepton number and baryon number while preserving their difference. Thus, a subtle excess of leptons could have dragged along a corresponding excess of baryons, leaving us with the matter-dominated universe we observe. This is a subtle and intricate dance of particles where the almost undetectable neutrino plays a pivotal role in shaping the very substance of galaxies. The role of the early universe's rapid expansion, a period known as cosmic inflation, also intertwines with these baryogenesis scenarios. Inflation, occurring a tiny fraction of a second after the Big Bang, smoothed out space-time and stretched quantum fluctuations into the seeds of future galaxies. It also provided a mechanism to drive the universe out of thermal equilibrium, a crucial condition for baryogenesis. During this period of exponential expansion, temperatures were extremely high, and the universe was a turbulent, dynamic environment. Any processes that broke symmetry, such as the decay of GUT particles or heavy sterile neutrinos, would have occurred in this rapidly expanding, non-equilibrium state, preventing matter and antimatter from simply annihilating back into pure energy. The expansion would have frozen in the tiny matter excess, preventing further annihilation and allowing it to persist and grow. Imagine a cosmic sculptor working quickly during a chaotic moment, carving out a subtle, enduring form that would eventually become everything we see. The search for answers continues across multiple fronts. Beyond the ongoing missions like AMS-02, future experiments are being designed to probe the properties of neutrinos with unprecedented precision. Projects such as the Deep Underground Neutrino Experiment, or DUNE, and Hyper-Kamiokande aim to detect subtle differences in the oscillations of neutrinos and antineutrinos, which could reveal further CP violation in the lepton sector. Such discoveries would lend significant support to leptogenesis theories. Furthermore, the next generation of particle accelerators will push the energy frontier even higher, seeking direct evidence for new particles predicted by theories beyond the Standard Model. These elusive particles, if found, could be the missing pieces in the baryogenesis puzzle, the ephemeral entities whose brief existence determine the fate of our matter-filled cosmos. As we reflect upon this cosmic mystery, it evokes a profound sense of our place in the universe. We are not merely observers of a static reality, but the conscious product of its intricate, dynamic history. The existence of every atom in our bodies, every star we see twinkling in the night, is a testament to a delicate imbalance that occurred in the earliest moments of time. We are a tiny, yet significant fraction of the universe's total energy and matter, a persistent echo of an ancient, almost imperceptible cosmic preference. This deep understanding that our very being is a consequence of fundamental physics can bring a quiet wonder and awareness that our existence is both fragile and profoundly connected to the grand evolving story of the cosmos. The universe, in its majestic unfolding, chose to favor matter, and in doing so, allowed for the emergence of complexity, consciousness, and the capacity for us to truly ponder its origins. The rigorous confirmation of CPT symmetry, revealing that antimatter is indeed a perfect, precise mirror image of matter, compels us to consider the subtle dynamics rather than static differences. If matter and antimatter are fundamentally equivalent in their properties, then the cosmic mystery of their imbalance must lie in the processes of the early universe, where some fleeting conditions favored matter. This understanding dispels the notion of antimatter being inherently alien or evil, instead framing it as a natural, symmetrical partner to all that we know. However, the absence of large-scale antimatter structures within our observable universe remains a puzzle that guides our ongoing cosmic detective work. One might naturally wonder if vast regions of the universe, perhaps distant galaxies, could be composed entirely of antimatter. Such a scenario would maintain the overall matter-antimatter balance, simply separating the two types of substance. Yet scientific observations strongly argue against this intriguing possibility. If there were such antimatter galaxies adjacent to matter-dominated ones, the boundaries between them would be zones of intense annihilation. The collision of matter and antimatter at these interfaces would produce copious amounts of high-energy gamma rays, forming a distinct and powerful signature that telescopes would undoubtedly detect. Surveys of the cosmos, including those by gamma-ray observatories, have meticulously searched for such signals. To date, no evidence of these characteristic annihilation events has been found on a galactic scale, which means that if antimatter galaxies exist, they must be incredibly far away, beyond the reach of our current observational limits, or separated by such immense voids that interactions are virtually non-existent. The data, however, overwhelmingly suggests that our observable universe is overwhelmingly matter-dominated, reinforcing the need for a mechanism that produced an excess of matter in the very beginning. Even in the profound emptiness of space, the concept of antimatter is not entirely absent. It exists as a fleeting, ephemeral presence, a testament to the dynamic nature of the quantum vacuum. According to quantum field theory, what we perceive as empty space is, in fact, a bubbling sea of virtual particles and antiparticles constantly winking into and out of existence. These pairs, such as an electron and a positron, spontaneously emerge from the vacuum for unimaginably brief moments, borrowing energy from the universe, only to annihilate each other and return to the void before they can be directly observed. This continuous quantum dance, a cosmic froth of creation and destruction, is a fundamental property of reality, providing a constant, if invisible, reminder of antimatter's ubiquitous presence. It is a quiet, energetic hum beneath the stillness, an invisible ballet that shapes the very fabric of space-time at its most fundamental level. The deliberate creation and study of antimatter in controlled laboratory environments offers a unique window into its properties and behavior. At CERN, using the antiproton decelerator, scientists routinely produce antiprotons by smashing high-energy protons into a target. These antiprotons are then slowed down, mixed with positrons, and carefully assembled into antihydrogen atoms. The challenge then becomes trapping these ephemeral antiatoms, as any contact with ordinary matter would result in immediate annihilation. Sophisticated magnetic traps, which utilize powerful magnetic fields, are employed to suspend the antihydrogen atoms, preventing them from touching the walls of their containment vessel. These experiments, such as ATRAP, ALPHA, and GBAR, allow physicists to perform incredibly precise measurements, comparing the spectral lines of antihydrogen with those of ordinary hydrogen. The goal is to detect any subtle differences, any minute deviations that could hint at a deeper, unknown physics, or a violation of the cherished CPT symmetry. So far, the results confirm the expected mirror image symmetry, with antihydrogen exhibiting the same quantum properties as its matter counterpart, as precisely as we can measure. The ability to create and manipulate antimatter, even in minuscule quantities, opens up intriguing, albeit distant, possibilities. While the notion of antimatter-powered spacecraft or weapons often belongs to the realm of science fiction, the fundamental research into antimatter's properties could have transformative implications. For instance, precisely measuring how antimatter responds to gravity is a crucial ongoing experiment. Does antihydrogen fall up or down? Current theories predict it should fall down, just like ordinary matter, upholding Einstein's equivalence principle. Experiments like GBAR at CERN are designed to test this prediction with extreme precision. Beyond fundamental physics, the unique energy release from matter-antimatter annihilation, the most efficient energy conversion known, sparks thoughts about future energy sources or propulsion systems, though the immense challenges of production and storage make these prospects very long-term. The true power of antimatter, however, lies in its capacity to illuminate the fundamental laws that govern our universe, pushing the boundaries of what we understand about existence itself. Our journey through the world of antimatter reveals a universe of profound duality and subtle asymmetry. From Dirac's initial theoretical prediction to the meticulous experiments at CERN, antimatter has transitioned from a mathematical curiosity to a tangible, albeit elusive, component of reality. The question of where it went remains one of physics' most captivating enigmas, leading us to consider whether our existence is a fortunate cosmic leftover, a minuscule triumph of matter over antimatter, or if there are still undiscovered realms where the balance is restored. This realization that our very being is predicated on such a delicate cosmic preference invites a quiet contemplation of the universe's intricate design, or perhaps its beautiful accidents. It suggests that even in the grand, silent expanse, the smallest imbalances can lead to the most magnificent outcomes, culminating in the complex tapestry of stars, galaxies, and conscious life that gazes back into the cosmic mirror. The exquisite precision of CPT symmetry tests at facilities such as CERN, where antihydrogen atoms are meticulously compared to their ordinary matter counterparts, offers a profound bedrock for our understanding. The results, consistently showing no detectable differences between matter and antimatter, reinforce a cornerstone of modern physics. The combined symmetries of charge conjugation, parity inversion, and time reversal must hold true. This means that if we were to reverse every particle's charge, reflect it in a mirror, and run time backward, the laws of physics would remain unchanged. Such a perfect symmetry ensures that antimatter is not an inherently exotic or fundamentally different substance, but merely a precise negative image of matter. This deep equivalence implies that the matter-antimatter imbalance which allowed our universe to exist must have arisen from dynamic processes, from conditions in the early cosmos that briefly favored matter, rather than from any intrinsic asymmetry in the particles themselves. This is a crucial distinction, shaping the direction of theoretical inquiry into the universe's earliest moments. One of the most intriguing questions surrounding antimatter and a direct test of fundamental principles is how it responds to gravity. Does antimatter fall up or down? According to Einstein's equivalence principle, a cornerstone of general relativity, all forms of mass energy should respond to gravity in the same way, regardless of their composition. This means that antimatter should fall downwards, just like ordinary matter. While this seems intuitively obvious, it is a prediction that must be rigorously tested, given the mirror image nature of antimatter. Experiments such as GBAR, the gravitational behavior of antihydrogen at rest, at CERN, are specifically designed to measure this. Scientists produce antihydrogen atoms and then carefully observe their acceleration in Earth's gravitational field. The challenge is immense, as antihydrogen atoms must be cooled to incredibly low temperatures, near absolute zero, and then held in a magnetic trap, preventing annihilation until they can be released and observed as they fall. These are not easy experiments, and the precision required pushes the limits of current technology. But the potential discovery of any deviation from the equivalence principle would be nothing short of revolutionary, demanding a fundamental rethinking of gravity itself and our understanding of space-time. Beyond these fundamental inquiries, the unique properties of antimatter spark imaginative discussions about its potential applications. The most compelling, perhaps, is the immense energy released during matter-antimatter annihilation, a process that converts mass into energy with 100% efficiency, far surpassing nuclear fission or fusion. A mere gram of antimatter annihilating with a gram of matter could, in theory, release enough energy to power a major city for years. This extraordinary energy density has led to speculative ideas about antimatter propulsion for interstellar travel, where tiny amounts of antimatter could provide the thrust needed to achieve velocities close to the speed of light, enabling journeys to distant stars within human lifespans. However, the immense challenges of producing, storing, and safely handling antimatter cannot be overstated. Current production methods yield only picograms, or trillionths of a gram, requiring vast amounts of energy and time. Storing antimatter, which must be kept isolated from all ordinary matter, requires complex magnetic fields and cryogenic temperatures. These technological hurdles are enormous, placing large-scale antimatter applications firmly in the distant future, if they are even achievable. Nevertheless, smaller-scale applications of antimatter are already a reality, demonstrating its tangible presence in our technological world. As we discussed, Chi are a prime example. The positrons emitted by carefully selected radioactive isotopes interact with electrons in the body, producing gamma rays that allow for detailed functional imaging of organs and tissues. This diagnostic tool has revolutionized medicine, offering insights into brain activity, cancer detection, and heart disease. Future medical applications might include targeted therapies, where antimatter could be used to precisely destroy cancerous cells, though this remains an area of ongoing research and significant technical challenge. The field of materials science also looks to antimatter for novel insights. The study of how positrons interact with different materials can reveal subtle defects and properties at the atomic scale, providing valuable information for developing new materials. These applications, though modest in scale compared to the grand visions of interstellar travel, highlight antimatter's inherent usefulness and its quiet integration into our scientific and technological endeavors. The very notion of antimatter, this mirror reflection of our world, invites us to contemplate the deeper structure of reality and our place within it. We exist in a universe born from a cosmic event that, by all accounts, should have left nothing behind but light. Yet a tiny, almost imperceptible asymmetry in the early moments of creation allowed a small surplus of matter to persist, forming everything from the smallest subatomic particles to the grandest galaxy clusters. This matter-dominated cosmos, where stars shine and life flourishes, is a testament to the universe's ability to transcend perfect symmetry, to create complexity from imbalance. As you reflect on these profound ideas, consider the delicate balance that underpins your own existence, the intricate dance of forces and particles that allows for consciousness itself. The universe, in its profound elegance, holds secrets that continue to unfold, inviting us to look deeper, to question further, and to find a quiet wonder in the fundamental laws that govern our shared reality. The universe, in its elegant adherence to fundamental symmetries like CPT, presents us with a captivating paradox. If matter and antimatter are indeed perfect mirror images, precise counterparts in every fundamental aspect, then the observed dominance of matter around us demands a deeper explanation than simple preference. This persistent mystery, often termed the baryonic asymmetry problem, has led physicists to consider grander, more speculative, yet mathematically consistent cosmological models. What if, rather than a single, perfectly balanced beginning that then tilted in favor of matter, the universe found an ingenious way to separate its matter and antimatter constituents into distinct regions, perhaps on a scale almost beyond our current human comprehension? Could the solution to the missing antimatter simply be that it is not truly missing, but merely residing in another cosmic neighborhood, far beyond our reach? One such intriguing hypothesis, often discussed in the quiet halls of theoretical physics, suggests the existence of vast antimatter domains. These would be sprawling cosmic territories, immense bubbles of existence stretching across billions of light-years, where antiprotons and anti-electrons or positrons coalesced to form stable antiatoms. These antiatoms would then gravitationally gather into anti-stars, burning with a mirror image brilliance, and eventually form entire anti-galaxies, rotating in a cosmic waltz of their own. In this ambitious scenario, the early universe could have indeed produced equal amounts of matter and antimatter, perfectly upholding the initial symmetry of the Big Bang, a moment of cosmic equilibrium. But then, through some intricate, perhaps yet undiscovered physical mechanism, these two cosmic counterparts became spatially segregated. This segregation might have occurred during the earliest, most turbulent moments of the Big Bang, perhaps driven by complex phase transitions as the fundamental forces of nature began to differentiate, much like water separating into ice and steam at critical points, or by the dynamics of exotic topological defects, such as cosmic strings or domain walls, acting as colossal cosmic sorting mechanisms, subtly pushing matter to one side and antimatter to the other. Imagine, if you will, the early cosmos as a vast churning ocean, where currents of nascent matter and antimatter slowly, imperceptibly, drift apart, eventually settling into their own isolated seas. For every luminous galaxy we observe, there might exist a dark, mirror image counterpart, silently drifting through the cosmic expanse, composed entirely of antimatter, a grand, silent reflection that we simply cannot perceive directly. A universe within a universe, yet forever separated by the sheer immensity of space. However, as we have touched upon in our previous reflections, direct observational evidence for such large-scale antimatter structures remains conspicuously absent. The most compelling test of this hypothesis lies in the meticulous search for the characteristic signatures of annihilation. If there were vast antimatter galaxies bordering matter-dominated ones, the interfaces between these regions would be zones of intense particle-antiparticle collisions. These collisions, moments of pure energy conversion following the profound principle of E equals mc squared. Background glow that our advanced gamma-ray observatories, such as the Fermi Gamma Ray Space Telescope, would undoubtedly detect. These instruments, acting as the universe's keenest eyes in the high-energy spectrum, have conducted extensive surveys of the cosmos, meticulously searching for such telltale signals. But to date, no pervasive gamma-ray background indicative of large-scale matter-antimatter annihilation has been found. This absence places severe constraints on the size and proximity of any potential antimatter domains. If they furthest reaches empty voids, that interactions are virtually non-existent, akin to two distant islands in an ocean so vast their shores never meet, their existence known only through the theoretical maps of physicists. At least in the regions we can probe with our instruments, is overwhelmingly matter-dominated, reinforcing the fundamental puzzle of the matter, antimatter asymmetry, and urging us to seek answers in the realm of subtle, rather than grand, cosmic separation. The concept of a mirror universe takes this idea of cosmic segregation a significant step further, venturing into the captivating and somewhat mind-bending landscape of the multiverse. It suggests not just separated domains within our own universe, but entirely distinct universes that are CPT conjugates of our own. In this radical but profoundly thought-provoking model, the entire multiverse, a grand ensemble or collection of many universes, could collectively uphold CPT symmetry, even if individual universes, like ours, exhibit an imbalance. Our universe, with its matter dominance and a specific, forward-moving arrow of time, might be balanced by another universe that is dominated by antimatter, and perhaps experiences time flowing in the opposite direction, or has its spatial coordinates inverted, a perfect cosmic negative. This is a profound and beautiful notion, one that elevates the principle of symmetry to the ultimate cosmic scale, suggesting that the missing antimatter isn't truly missing in the grand cosmic ledger, but simply exists elsewhere, in a reality that is its perfect yet inverted reflection. It allows for local asymmetry within a global symmetry, a kind of cosmic balancing act played out across an infinite ensemble of realities, where every possible permutation of fundamental laws might find its expression. A symphony of diverse physical realities that together form a harmonious whole, eternally bound, yet eternally separate. This journey into the nature of antimatter ultimately brings us back to the profound interplay between symmetry and asymmetry, at the very heart of physical reality itself. It is the subtle breaking of perfect symmetry in the early universe, a tiny bias of just one matter particle for every billion matter-antimatter pairs that annihilated, that allowed for the emergence of all the structure and complexity we observe around us today. Had the balance been perfectly maintained, a universe of pure radiation, eternally hot and featureless, devoid of matter, of stars, of planets, and ultimately of life, would have been our inevitable fate. Yet the underlying CPT symmetry, which ensures the fundamental equivalence of particles and antiparticles under these combined transformations, provides a deep, reassuring order to the apparent chaos of creation. It is a testament to the universe's intricate design, where fine-tuned conditions and delicate deviations from perfect balance give rise to the rich tapestry of existence. Our ability to even ponder these questions, to formulate elegant theories about cosmic sorting mechanisms or mirror universes, and to embark on meticulous experimental searches for the subtle echoes of antimatter, is itself a direct and marvelous consequence of this cosmic unfolding. We are, in a sense, the universe's way of observing, questioning, and appreciating its own miraculous matter-dominated state, a brief luminous flicker in the vast, quiet cosmic theater. As you reflect upon these grand ideas, allow your consciousness to drift through the vast, silent spaces where matter and antimatter might once have met, or perhaps still exist in their separate, mirrored realms. Allow yourself to fundamental. You, a complex collection of matter, are a living testament to a cosmic choice, a subtle tilt in the scales of existence that allowed awareness to emerge and flourish. In this profound dance of creation and annihilation, of symmetry and its beautiful breaking, we find ourselves momentarily aware, gazing into the vastness, seeking to understand the fundamental reflections of our world and the silent, elegant laws that govern its very being. May these thoughts guide you to a restful and insightful slumber. The persistent enigma of our matter-dominated universe, despite the elegant CPT symmetry that dictates antimatter is a perfect mirror of matter, continues to guide our deepest inquiries. This cosmic imbalance, where matter triumphed over antimatter in the early moments of existence, requires a dynamic explanation, a subtle deviation from perfect equilibrium. The standard model of particle physics, while remarkably successful, does not inherently provide enough of the necessary ingredients, specifically sufficient CP violation and baryon number violation, to account for the vast asymmetry we observe. This necessitates a journey beyond our current most precise theories into realms of hypothetical particles and grander cosmic processes. One such theoretical framework that seeks to address this profound question is electroweak baryogenesis. Unlike grand unified theories which propose new physics at extremely high energies, electroweak baryogenesis suggests that the matter-antimatter asymmetry could have been generated during a specific phase transition in the early universe known as the electroweak epoch. This epoch, occurring when the universe was a mere 10 picoseconds old, saw the electroweak force, a unification of electromagnetism and the weak nuclear force, separate into the distinct forces we recognize today. This transition, much like water turning into steam, would have created a non-equilibrium environment. If, during this phase change, there were sufficient CP violation from new physics beyond the standard model, perhaps involving interactions with the Higgs field, a slight excess of baryons could have been frozen in. The specific conditions of the expanding universe at that precise moment would have prevented the newly formed matter-antimatter pairs from completely annihilating, leaving behind the minuscule matter surplus that would eventually form all the structures we see. This theory offers an elegant alternative to earlier, higher-energy baryogenesis models, suggesting that the critical moments for our existence might have unfolded at a somewhat later, yet still unimaginably early, stage of cosmic evolution. This profound search for the origin of matter also leads us to consider the subtle role of fundamental constants. These are the unchanging numbers that define the strength of forces, the masses of particles, and the very fabric of space-time. If these constants were even slightly different, the delicate balance required for baryogenesis might not have occurred, or the resulting matter excess could have been too small or too large to allow for the formation of stable structures like stars and galaxies. For instance, the precise values of quark masses and mixing angles, which govern their interactions and decays, are crucial for the amount of CP violation observed. Any alteration could have drastically changed the outcome of the early universe. This fine-tuning, this remarkable precision in the universe's fundamental parameters is not a dramatic event, but a quiet, underlying condition that allowed for our existence. It suggests an intricate cosmic dance where every step, every constant, plays a role in the grand choreography of reality. It is also important to clarify a common misconception. Antimatter is not dark matter. While both are mysterious components of the universe, their natures are fundamentally different. Antimatter consists of particles that are essentially mirror images of ordinary matter, possessing the same mass but opposite charge and quantum numbers. They interact with light and other forces in predictable ways, and when they meet their matter counterparts, they annihilate, producing detectable bursts of energy. Dark matter, on the other hand, is a hypothetical form of matter that does not interact with light or other electromagnetic forces at all. It does not annihilate with ordinary matter in the same way, and its presence is inferred solely through its gravitational effects on visible matter. Scientists believe dark matter constitutes about 27% of the universe, a cosmic scaffolding that holds galaxies together. So, while antimatter offers a compelling puzzle about the origin of our visible world, dark matter presents an entirely separate, equally profound mystery about the unseen mass that shapes the cosmos. The ultimate resolution to the matter-antimatter asymmetry may lie in the realm of the multiverse, a concept we briefly touched upon. If our universe is but one of an infinite ensemble of realities, then perhaps the overall CPT symmetry is preserved across this vast collection. Our particular universe might simply be one bubble where matter happened to dominate, while other universes, perhaps an equal number, are dominated by antimatter. This grander perspective offers a way to reconcile the observed local asymmetry with a global, overarching symmetry of the laws of physics. Each universe in this cosmic tapestry could have arisen from its own unique set of initial conditions or undergone different symmetry-breaking processes, leading to a diverse range of outcomes. Such a model, while currently beyond direct experimental verification, offers a philosophical elegance, suggesting that the missing antimatter is not lost, but simply exists in other realities, forever separated from our own, yet collectively contributing to the cosmic balance. It transforms our universe from a singular, unique event into one thread in an infinitely rich and varied cosmic fabric. The ongoing quest to understand antimatter and its cosmic disappearance is a testament to the enduring curiosity of humanity. From the precise measurements of antihydrogen at CERN, seeking any minute deviation from symmetry, to the deep space probes searching for distant echoes of antimatter galaxies, and the theoretical physicists developing new models for baryogenesis, The pursuit of this fundamental mystery continues to push the boundaries of our knowledge. Each new piece of data, each refined theory, brings us a step closer to understanding the conditions that allowed for our existence. This realization that our very presence is woven into the fabric of these cosmic questions can evoke a sense of quiet wonder. We are not merely transient beings, but conscious participants in the universe's grand narrative, reflecting upon its deepest symmetries and its most profound imbalances. May these thoughts carry you gently into a world of serene sleep. Our ongoing quest to comprehend the universe's profound matter-antimatter asymmetry continues to lead us down fascinating pathways, far beyond the initial observations of particle physics. The Standard Model, while a triumph of human intellect, provides only a partial answer to the cosmic riddle of why matter predominates. The observed CP violation within its framework, though crucial, is simply not potent enough to explain the vast surplus of matter that allowed for stars, galaxies, and life to emerge. This realization compels physicists to look for deeper sources of symmetry breaking, mechanisms that existed in the universe's earliest, most energetic moments, hinting at a physics yet to be fully discovered. Many theoretical extensions to the Standard Model propose new particles and interactions that could provide the necessary CP violation. One prominent example is supersymmetry, often abbreviated as SUSY. SUSY postulates that for every known particle, there exists a heavier superpartner. So, for an electron, there would be a selectron, and for a photon, a photino. These hypothetical superpartners, if they existed in the early universe, would naturally introduce new phases of CP violation, far beyond what the Standard Model allows. Their interactions and decays could have provided the crucial imbalance required for baryogenesis, the process that generated the observed excess of matter. While SUSY particles have not yet been directly detected, experiments at the Large Hadron Collider continue to search for their subtle signatures, pushing the boundaries of our understanding of fundamental reality. Imagine a hidden layer to existence, a parallel set of particles that once danced into being, subtly influencing the cosmic scales before fading from our direct perception, leaving behind only the echoes of their transformative influence. The fundamental CPT theorem, a cornerstone of quantum field theory and special relativity, states that the laws of physics are invariant under a combined transformation. This means that if CP symmetry is violated, as we have observed, then time reversal, or T-symmetry, must also be violated to maintain the overall CPT invariance. What does a violation of T-symmetry truly mean? It implies that certain physical processes would not proceed identically if time were run backward. Imagine watching a film of a particle decay and then watching it in reverse. If T-symmetry holds, the reverse process would be physically indistinguishable from a plausible forward process. However, if T-symmetry is violated, the reversed film would clearly show an impossible or highly improbable event. This subtle, directional bias in the fundamental interactions of particles is not about time literally flowing backward, but rather about the inherent irreversibility of certain quantum processes. It speaks to a fundamental arrow of time woven into the very fabric of particle interactions, a microscopic bias that echoes the macroscopic arrow of time we experience in the universe's expansion and the increase of entropy. It is a profound connection, linking the smallest quantum events to the grandest cosmic narratives. The search for this deeper CP and T-symmetry violation is a critical frontier in experimental physics. One of the most sensitive probes involves measuring the electric dipole moments, or EDMS, of elementary particles like electrons and neutrons. An EDM is a measure of the separation of positive and negative charges within a particle, and its existence would indicate a fundamental asymmetry in the particle's internal structure, a subtle preference for one direction over another. According to the Standard Model, the EDMS of these particles should be vanishingly small, almost zero. However, many theories beyond the standard model, such as supersymmetry, predict much larger, yet still incredibly tiny, EDMS. Experiments are constantly pushing the limits of precision, seeking to detect these elusive moments. If a non-zero EDM were to be discovered, it would be a clear and unambiguous signal of new physics and a direct observation of CP and T symmetry violation beyond what we currently understand, providing a vital clue in the baryogenesis puzzle. These measurements are exquisitely challenging, requiring the isolation of particles from all external influences in environments of extreme stillness and cold, a quiet vigil for the universe's most subtle secrets. Another promising avenue for uncovering additional CP and T symmetry violation lies in the continued study of neutrinos. As we discussed, leptogenesis theories propose that an asymmetry in the lepton sector involving heavy neutrinos could have led to the matter dominance. Experiments like DUNE and hyperkamiokande are designed to precisely measure the oscillation patterns of neutrinos and antineutrinos as they travel over long distances. If there are subtle differences in these oscillation rates, it would be a direct indication of CP violation in the lepton sector, a profound confirmation of leptogenesis. Such a discovery would not only illuminate the origin of matter, but also provide crucial insights into the nature of neutrinos themselves, these ghostly particles that hold so many of the universe's deep secrets. These colossal detectors, often buried deep underground to shield them from cosmic noise, are patiently waiting, like vigilant sentinels, for the whispers of cosmic asymmetry to reveal themselves. As we gently drift through these profound concepts, consider the delicate balance that underpins all of existence. The universe, in its grand design, began with a near-perfect symmetry between matter and antimatter. Yet it was the subtle, almost imperceptible breaking of this symmetry, a cosmic preference encoded in the fundamental laws, that allowed for the emergence of complexity, structure, and ultimately, consciousness. Every atom in your body, every star in the night sky, is a testament to this delicate cosmic choice, a reminder that even the smallest deviations from perfection can lead to the most magnificent and enduring outcomes. Living, breathing consequence of this ancient cosmic asymmetry, a brief but luminous pattern in the vast, silent dance of particles and forces. This deep connection, this awareness that our existence is intertwined with the universe's deepest mysteries, can bring a profound sense of calm and wonder, allowing your thoughts to settle as gently as starlight upon a tranquil sea. The enduring mystery, profound implications of CPT symmetry, steadfastly upheld in every experimental test to date, continue to shape our understanding of antimatter. This fundamental theorem, asserting that the laws of physics are identical for particles and antiparticles when mirrored in space and reversed in time, means that antimatter is not merely an inverse, but a perfectly symmetrical reflection of matter. Therefore, the cosmic riddle of matter's overwhelming dominance cannot be attributed to answer must lie in dynamic processes that occurred during the universe's infancy. Fleeting moments when the conditions allowed for a subtle, yet decisive, breaking of these symmetries, favoring the creation of matter. This necessitates a continued exploration of physics beyond the well-established standard model, pushing the boundaries of our knowledge into the unknown. The quest for these deeper sources of symmetry breaking often leads to theoretical constructs involving phenomena that existed only in the extreme energy conditions of the very early universe. Consider, for instance, the possibility of additional, heavier Higgs bosons. The Higgs field, which permeates all of spacetime and gives particles their mass, underwent a pivotal phase transition shortly after the Big Bang. If there were multiple types of Higgs bosons, or if the Higgs field had a more complex structure than currently understood, this phase transition could have been far more intricate, creating regions of space where different CP violating interactions were favored. Such a scenario could provide the necessary environment for electroweak baryogenesis to efficiently produce the observed matter-antimatter asymmetry. These hypothetical particles, if they existed, would have been incredibly massive and short-lived, quickly decaying as the universe cooled, leaving no direct trace in the present cosmos. Their influence, however, would be etched into the very fabric of our matter-dominated existence, a silent testament to their fleeting yet crucial role in shaping reality. Another captivating, albeit speculative idea that complements the baryogenesis puzzle involves the concept of extra-spatial dimensions. If our universe is not limited to the 3 spatial dimensions we perceive, but contains additional curled-up dimensions, these extra dimensions could have played a role in the early universe's evolution. It is conceivable that interactions propagating through these hidden dimensions, or particles with access to them, could exhibit different CP-violating properties. During the intense, high-energy conditions of the Big Bang, these extra dimensions might have been more accessible, allowing for unique particle interactions that subtly favored matter. As the universe expanded and cooled, these extra dimensions would have compactified, becoming too small to be directly observed, but leaving behind their imprint on the matter-antimatter balance. This idea, often explored within the framework of string theory and M-theory, paints a picture of a multidimensional cosmos where the very geometry of space could have influenced the fundamental properties of particles, subtly tipping the scales in favor of matter. The search for primordial antimatter continues to be a crucial experimental endeavor, providing vital constraints on these theoretical models. Aboard the International Space Station, meticulously scans cosmic rays for any signs of antihelium or heavier antinuclei. The non-detection of such particles, despite years of operation, strongly indicates that if large antimatter domains exist, they are not close enough to interact with our matter-dominated regions, or are separated by such immense empty voids that any annihilation signals are too faint to observe. This observational constraint reinforces the idea that the matter-antimatter asymmetry is a global feature of our observable universe, rather than a local phenomenon. The data guides our theories, gently nudging us away from models that predict easily detectable antimatter clusters and towards those that explain its absence through a primordial imbalance. Ultimately, the resolution of the baryonic asymmetry problem is one of the most profound goals of modern physics. It is a quest that intertwines particle physics, cosmology, and the very nature of space-time itself. Understanding why matter exists in such abundance and where its symmetrical counterpart disappeared to is not merely an academic exercise. It is a journey to comprehend the fundamental conditions that made our existence possible. Every atom in our bodies, direct consequence of this cosmic preference for matter. We are, in a very real sense, the universe's self-reflection, a conscious assembly of particles pondering its own origins. This deep connection between the grand cosmic narrative and our individual existence can evoke a profound sense of wonder and intellectual satisfaction. It reminds us that even in the vast, this enduring mystery, so central to our understanding, invites a quiet contemplation. Our journey through the mirror world of antimatter, from its initial theoretical prediction to the profound enigma of its cosmic disappearance, has led us to ponder the very origins of our matter-dominated universe. We have seen how the delicate balance of fundamental symmetries, particularly CPT, shapes our understanding, and how the subtle breaking of these symmetries in the universe's earliest moments allowed for the emergence of all that we know. Whether through the intricate dance of electroweak baryogenesis, the speculative elegance of supersymmetry, or the vast, perhaps segregated realms of a multiverse, the quest for the missing antimatter is a quest to understand why we exist. It is a humbling thought, isn't it? That our entire existence, every atom in our bodies, every star that twinkles in the tranquil night sky, is a direct consequence of a minuscule cosmic preference for matter, a 1 in a billion triumph that allowed complexity and consciousness to flourish. This intricate cosmic architecture, born from a universe that should, by all accounts, have been a silent sea of pure radiation, is a profound testament to the power of fundamental laws and their subtle, yet magnificent, exceptions. The ongoing scientific pursuit, whether through or the vast cosmic surveys, is humanity's way of gazing into this cosmic mirror, seeking not just answers, but a deeper appreciation for the intricate story of our reality. May these deep thoughts about antimatter and the profound origins of our universe carry you into a world of tranquil sleep. Remember that the universe is amazing, and you are a part of its most fundamental and beautiful mysteries. Fall asleep with this feeling of serenity and endless knowledge. Good night. Our journey tonight begins with a profound cosmic enigma, the peculiar observation that the universe as we perceive it is far less substantial than its gravitational behavior suggests. For centuries, our understanding of the cosmos was built upon what we could directly observe: the shimmering stars, the luminous galaxies, the vast nebulae of gas and dust. Yet, as our instruments grew more sophisticated, peering ever deeper into the cosmic tapestry, a subtle, persistent discrepancy began to emerge. It was as if a grand celestial orchestra was playing, but many of its most powerful instruments remained unseen, their profound influence felt only through the resonant vibrations they imparted upon the visible symphony. This unseen component, this silent gravitational architect, is what we now refer to as dark matter, a term that evokes both mystery and the vastness of our current ignorance, challenging our very definition of what matter truly is. The first faint whispers of this invisible presence surfaced in the 1930s through the pioneering work of an often eccentric yet brilliant Swiss astronomer named Fritz Zwicky. He was meticulously studying the Coma Cluster, a truly colossal aggregation of thousands of galaxies, all bound together by the invisible threads of gravity. With his keen observational skills, Zwicky measured the velocities of individual galaxies hurtling through this immense structure. What he discovered was deeply perplexing. These galaxies were moving at speeds far exceeding what could be accounted for by the gravitational pull of all the visible matter, the stars and gas, that he could detect. Based on their luminosity, the cluster simply did not possess enough mass to prevent its energetic members from flying apart, scattering into the cosmic void. Yet they remained gravitationally bound, orbiting each other in a stable, coherent, and surprisingly rapid dance. To reconcile this profound discrepancy, Zwicky courageously posited the existence of some unseen, non-luminous mass, which he rather aptly termed dark matter. This was a truly radical notion for its time, suggesting that the familiar components of the universe, the atoms that make up stars, planets, and indeed ourselves, represented only a small fraction of its true contents. His idea, though groundbreaking and prescient, remained largely on the periphery of scientific thought for several decades, a quiet, almost forgotten hypothesis awaiting more compelling evidence. It wasn't until the 1970s that the evidence for dark matter began to solidify into an undeniable scientific imperative, largely thanks to the meticulous and persistent work of astronomer Vera Rubin and her colleague Kent Ford. They turned their gaze to the intricate ballet of individual spiral galaxies. Imagine, if you will, a vast cosmic pinwheel, its luminous arms slowly and majestically turning. Conventional Newtonian physics, based on the visible mass, predicted that the stars at the very outer edges of these galaxies, being farther from the gravitational center, should orbit much more slowly than those closer to the core. This is analogous to how the outer planets in our own solar system move more leisurely in their vast orbits than the inner ones. However, Rubin's precise spectroscopic measurements, which allowed her to determine the orbital speeds of stars at varying distances from the galactic center, revealed something astonishingly different. She consistently found that stars at the very fringes of galaxies were orbiting at roughly the same unexpectedly high speed as stars much closer to the luminous core. This flat rotation curve, as it came to be known, was a profound challenge to established physics. It unequivocally implied that there had to be a significant amount of invisible mass extending far beyond the luminous boundaries of the galaxy, creating an enormous and pervasive gravitational halo. This unseen mass provided the necessary additional gravitational pull to keep the outer stars from being flung into the cold, intergalactic space. Without this mysterious, invisible component, galaxies simply could not hold themselves together in the coherent, spiraling structures we observe. Their observations, confirmed by countless independent studies and advanced astronomical techniques, since transformed dark matter from a speculative idea into an undeniable, gravitationally active reality, a silent, ubiquitous partner in the formation and evolution of every galaxy we behold. So, with this compelling and ever-growing body of evidence, the question naturally arises: what exactly is this elusive dark matter? Scientists are now quite confident that it is not composed of ordinary baryonic matter, the familiar protons, neutrons, and electrons that form atoms, construct planets, and make up our very bodies. If it were, we would expect it to interact with light in some way, either absorbing, emitting, or reflecting it, which would, by definition, make it visible, or at least detectable through its interaction with the electromagnetic spectrum. Instead, dark matter interacts with the visible universe almost exclusively through gravity, a force that reaches across the vast cosmic distances with silent, unwavering authority. It passes through us, through our planet, and through stars without leaving a trace, like a silent, ghostly wind blowing through the very fabric of existence, utterly indifferent to our presence. Current theories, born from decades of intense research and theoretical development, suggest it is likely made up of some new, exotic type of subatomic particle that does not interact with the electromagnetic force, nor with the strong or weak nuclear forces, save perhaps for incredibly feeble interactions. Leading candidates for these mysterious particles include weakly interacting massive particles, or WIMPs, which would be many times heavier than a proton, yet incredibly elusive, like cosmic phantoms. Another class of hypothetical particles are axions, much lighter and even more weakly interacting, almost imperceptible to our current methods. Despite decades of dedicated experiments, from deep underground detectors shielding against the incessant barrage of cosmic rays, to sophisticated instruments aboard space telescopes designed to catch the faintest whisper of interaction, direct detection of these dark matter particles remains one of the greatest and most challenging quests in modern physics. We are, in essence, searching for shadows with mass, trying to grasp an entity that fundamentally defies our usual methods of observation, a silent, invisible component woven into the very structure of the cosmos. The profound evidence for dark matter extends far beyond the intricate ballet of galactic rotation. Consider for a moment the mesmerizing phenomenon of gravitational lensing. Just as a conventional glass lens bends and focuses light, truly massive objects in space possess the power to warp the very fabric of space-time around them. This curvature, accurately predicted by Einstein's theory of general relativity, causes light from more distant objects to bend as it passes by these massive foreground structures. This cosmic distortion can manifest in spectacular ways, creating distorted, magnified, or even multiple, ghostly images of background galaxies. When astronomers meticulously observe distant galaxy clusters, they consistently find that the amount of light bending or lensing is far greater than what can be accounted for by the visible matter alone. The immense gravitational pull required to produce such significant lensing effects points overwhelmingly to the pervasive presence of vast quantities of dark matter acting as an invisible cosmic magnifier, a lens made of pure, unseen gravity. These ghostly gravitational fields reveal themselves through the elegant bending of light, painting a vivid, albeit indirect, picture of the universe's hidden mass, a silent testament to its profound and pervasive influence. Furthermore, the very large-scale structure of the cosmos itself, the majestic way galaxies and galaxy clusters are arranged into a vast, intricate, cosmic web of luminous filaments interspersed with enormous empty voids, is deeply dependent on the gravitational influence of dark matter. In the incredibly early moments after the Big Bang, the universe was almost perfectly smooth, a uniform sea of energy and particles with only minuscule fluctuations in density. Ordinary baryonic matter, being subject to intense pressure from the omnipresent radiation, could not have collapsed quickly enough under its own gravity to form the colossal complex structures we observe today, such as galaxy clusters and superclusters. Dark matter, however, was immune to this radiation pressure. Being non-interacting with light, it could begin to clump together much earlier in the universe's history, forming gravitational potential wells that acted as the crucial seeds for the subsequent accumulation of ordinary matter. Imagine an invisible scaffolding, a grand cosmic skeleton upon which the luminous galaxies and clusters we see today slowly congealed and grew, pulled into shape by an unseen hand. The meticulous analysis of the cosmic microwave background, the ancient relic radiation from the Big Bang, provides further profound corroboration of this narrative. The precise patterns of temperature fluctuations in this primordial light are best explained by sophisticated cosmological models that explicitly include a significant component of dark matter, influencing the early universe's density perturbations and setting the stage for all subsequent structure formation. So, as we gaze at the tranquil night sky, dotted with countless luminous stars and galaxies, it is a profound thought to consider that what we see is merely a shimmering, delicate veneer upon a much grander, largely unseen structure. Our very existence, the intricate formation of our solar system, our galaxy, and indeed all known cosmic structures, is intimately interwoven with this invisible scaffolding. Dark matter, silent and elusive, yet gravitationally dominant, orchestrates a substantial portion of the cosmic dance, holding galaxies together, shaping the large-scale architecture of the universe, providing the fundamental gravitational embrace that allows for the emergence of complexity and, ultimately, for life itself. It is a powerful reminder that reality often extends far beyond the immediate grasp of our senses, inviting us to look deeper, to feel the subtle, yet undeniable, pull of the unseen. In this vast dark ocean of gravitation, we are but small luminous currents, flowing within its unseen depths, connected to a hidden grandeur that whispers of profound mysteries yet to be fully unveiled, prompting us to ponder our place within this grand, invisible design. The silent embrace of dark matter holds the universe in its grasp, and in a very real sense holds us too. While dark matter acts as an invisible gravitational sculptor, intricately shaping the cosmic web and holding galaxies in their wondrous dance, the universe harbors an even more profound and unsettling mystery, one that governs its ultimate expansion and fate: dark energy. If dark matter can be thought of as a silent, attractive force pulling things together with its unseen mass, then dark energy is its conceptual opposite: a pervasive, repulsive influence, gently yet relentlessly pushing the very fabric of space-time apart. This force, far more dominant in the grand cosmic budget, was not even a whisper in scientific thought until a relatively recent and truly astonishing discovery in the late 1990s, which fundamentally reshaped our understanding of the cosmos and our place within its unfolding story. The story of dark energy truly begins with a meticulous quest to measure the expansion rate of the universe. For decades, cosmologists generally assumed that the universe's expansion, set in motion by the Big Bang, must be gradually slowing down due to the collective gravitational pull of all the matter within it. It was a logical expectation, akin to a ball thrown upwards, eventually decelerating under Earth's gravity. To test this hypothesis, two independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, embarked on a mission to observe distant supernovae. Specifically, they focused on a particular type of stellar explosion known as Type 1a supernovae. These celestial beacons are remarkably consistent in their peak luminosity, acting as standard candles across the vast cosmic distances. By measuring how bright they appeared from Earth, astronomers could accurately calculate their distances, and by observing their redshift, they could determine how fast their host galaxies were receding. The results, when they finally emerged from years of painstaking observation and analysis, were nothing short of revolutionary and utterly unexpected. Instead of finding that the distant supernovae were receding more slowly, indicating a decelerating universe, both teams independently concluded the opposite. The expansion of the universe was not slowing down, but was, in fact, accelerating. This was a truly astounding revelation, forcing a radical reevaluation of our most fundamental cosmological models. The universe was not merely expanding, it was doing so at an ever-increasing rate, as if some unseen, pervasive force was actively pushing space apart, countering and ultimately overcoming the attractive pull of gravity. This mysterious, repulsive force was given the placeholder name dark energy, a label that acknowledges its profound influence while simultaneously highlighting our deep ignorance regarding its true nature. So, what exactly is this dark energy that so powerfully dictates the universe's destiny? The truth is, we do not yet know with certainty. It remains one of the most significant unsolved puzzles in all of modern physics, a profound challenge to our understanding of the fundamental laws of nature. However, several leading hypotheses attempt to explain its enigmatic properties. The most straightforward and perhaps the simplest explanation posits that dark energy is an intrinsic constant property of space itself, a kind of energy of the vacuum. This concept is often linked to Einstein's cosmological constant, a term he originally introduced into his equations of general relativity to achieve a static universe, a notion he later famously called his biggest blunder after Edwin Hubble discovered the universe's expansion. Ironically, the cosmological constant has re-emerged as the leading candidate for dark energy. If space inherently possesses this energy, then as space expands, more space is created, and with it, more of this vacuum energy, leading to a self-perpetuating acceleration. It's as if the very emptiness of space is imbued with a subtle yet powerful outward push, a quiet, ceaseless expansionary hum. Alternatively, dark energy might be a more dynamic, evolving field, not constant, but changing over cosmic time. This hypothetical entity is sometimes referred to as quintessence, a fifth fundamental force, distinct from gravity, electromagnetism, and the strong and weak nuclear forces. Such a field would behave differently from the cosmological constant, with its density and repulsive strength potentially varying as the universe evolves. Yet another intriguing, albeit more speculative possibility suggests that dark energy might be a manifestation of extra dimensions of space, or perhaps a consequence of modifications to Einstein's theory of gravity on the largest cosmic scales. Despite the variety of theoretical frameworks, the defining characteristic of dark energy remains its negative pressure, which allows it to exert a repulsive force, causing space to stretch faster and faster. This is a property unlike any known form of matter or radiation, underscoring its truly alien nature. The implications of dark energy's accelerating push are profound. Painting a contemplative, if somewhat stark, picture of the universe's distant future. If dark energy continues to dominate, as current observations strongly suggest, it implies an ultimate fate for our cosmos often referred to as the heat death or Big Freeze. In this scenario, the accelerating expansion will cause galaxies to recede from one another at ever-increasing speeds, eventually moving beyond each other's observable horizons. Imagine standing on a cosmic island, watching all the other islands drift away faster and faster until their light can no longer reach you, leaving you in an ever larger, emptier expanse. Our own Milky Way galaxy, along with its closest gravitational companions in the local group, would remain bound, but all other galaxies would eventually vanish from our sight. Their light stretched to such extreme wavelengths by the expansion of space that they would become effectively invisible. unobservable. Over incomprehensibly vast timescales, stars would exhaust their fuel, black holes would slowly evaporate through Hawking radiation, and even protons might eventually decay. The universe would become an incredibly cold, dilute, and dark place, a vast expanse of near-nothingness, where the average temperature approaches absolute zero and all organized energy is dissipated. In this distant, silent future, there would be no sources of light, no heat, no structure, and no activity. With no events to mark the passage of time, the very concept of time itself might lose its meaning, fading into an eternal, unchanging, frozen stillness. It is a future not of dramatic collapse or fiery end, but of a gentle, drawn-out fade, a slow dispersal into an infinite, desolate quietude. This is not a catastrophic event, but rather a majestic, drawn-out process, a natural consequence of the universe's fundamental dynamics. This pervasive, invisible force, dark energy, now constitutes approximately 68% of the total mass energy content of the universe, dwarfing both ordinary matter, which makes up only about 5%, and even dark matter, around 27%. This means that the universe we inhabit, the galaxies we admire, the planets we explore, and the very atoms that compose our bodies are merely a small, luminous froth on a vast, unseen ocean of dark energy and dark matter. We are, in a profound sense, living within a universe largely governed by entities we cannot see, cannot touch, and whose true nature we are only just beginning to grasp. This realization can evoke a sense of deep wonder, a quiet contemplation of the immense scales and hidden forces at play in the cosmos. To know that our present existence, our thoughts, our awareness, are unfolding within a fleeting moment of cosmic history, a brief golden age before the universe's eventual gentle dispersal, invites a unique perspective on the preciousness and transient beauty of our reality. The silent, accelerating push of dark energy reshapes our destiny, reminding us that the universe is a grand narrative still being written, its final chapters yet to be revealed, and we are but humble witnesses to its unfolding mystery. We have journeyed through the unseen gravitational embrace of dark matter and contemplated the relentless, accelerating push of dark energy, forces that together paint a grand, if somewhat sobering, picture of our cosmic destiny. These two mysterious constituents, distinct in their actions yet profoundly interconnected in their influence, dominate the very fabric of our universe. They represent a staggering 95% of its total mass energy content, leaving ordinary baryonic matter, the stuff of stars, planets, and ourselves, as a mere 5%, a luminous whisper in an overwhelmingly dark cosmos. This cosmic inventory, a revelation of the last few decades, is perhaps one of the most humbling and profound discoveries in the history of science, inviting us to reconsider our assumptions about what reality truly entails on the grandest scales. It is a quiet testament to how much remains veiled, patiently awaiting our diligent inquiry. This current understanding of the universe's composition and evolution is encapsulated within what cosmologists call the lambda-CDM model. Lambda, represented by the Greek letter, stands for the cosmological constant, our leading candidate for dark energy, embodying the vacuum energy of space itself. CDM stands for cold dark matter, referring to the hypothetical particles that move relatively slowly and interact only weakly with ordinary matter, providing the gravitational scaffolding for galaxies and larger structures. This model, despite the profound mystery surrounding its primary components, has proven remarkably successful. It elegantly and precisely explains a vast array of cosmological observations, from the subtle temperature fluctuations in the cosmic microwave background radiation, the afterglow of the Big Bang, to the observed large-scale distribution of galaxies across billions of light-years, forming the grand cosmic web. It is a testament to the power of scientific inquiry that we can build such a robust framework, even while acknowledging that its most fundamental pillars remain largely enigmatic. The Lambda CDM model serves as our current best description of the universe, a magnificent theoretical construct that guides our explorations even as it underscores the vast frontiers of the unknown, prompting new questions with every answer it provides. The quest to unveil the true nature of dark matter and dark energy is, therefore, one of humanity's most ambitious scientific endeavors, demanding ingenuity and perseverance. For dark matter, the search is multifaceted and relentless. Deep underground laboratories, shielded from the constant barrage of cosmic rays, house incredibly sensitive detectors designed to capture the faintest interaction of a dark matter particle, should it ever collide with an atom of ordinary matter. Imagine vast vats of supercooled liquid xenon or germanium crystals, waiting in profound silence for a single, elusive event. A tiny ripple in the detector's quiet vigil, a fleeting echo of the unseen. Particle accelerators, such as the Large Hadron Collider, are also pushing the boundaries of energy, attempting to create these hypothetical dark matter particles in controlled, high-energy collisions, hoping to glimpse their fleeting existence or reveal new fundamental forces. Beyond Earth, space-based observatories continue to map the cosmic web with unprecedented precision, seeking subtle clues in the gravitational lensing patterns and the distribution of galaxies that might further constrain the properties of dark matter, slowly narrowing the possibilities of its true identity, piece by quiet piece, guiding us toward a deeper understanding of this ubiquitous, invisible presence. The pursuit of dark energy is equally intricate, though different in its methodology, as we cannot hope to detect a pervasive property of space in the same way we might a particle. Instead, astronomers continue to meticulously survey distant Type 1, a supernovae, refining their measurements of the universe's accelerating expansion, pushing the limits of observation to probe the cosmic past. Each new distant supernova acts as another data point, painting an ever-clearer picture of dark energy's influence across cosmic time, helping us to understand if its strength has remained constant or if it has subtly evolved, perhaps hinting at a dynamic cosmic fluid. High-resolution maps of the cosmic microwave background continue to be scrutinized with extraordinary care, searching for any anomalies or subtle signatures that might reveal the true nature of the cosmological constant, or hint at a more dynamic quintessence, a shifting field that permeates everything. Furthermore, large-scale galaxy surveys, meticulously charting the positions and movements of hundreds of millions of galaxies, provide crucial insights into the growth of cosmic structures, offering another window into the intricate interplay between gravity and the repulsive force of dark energy. These diverse approaches, spanning the subatomic to the supergalactic, are all part of a grand, coordinated effort to decipher the universe's hidden language, to understand the fundamental forces that shape not only its past and present, but also its ultimate, serene future. This journey into the unseen realms of dark matter and dark energy reveals a universe far more mysterious and magnificent than our ancestors could have ever conceived. It is a cosmos where the familiar elements that compose us and our world are but a minor component, overshadowed by forces and substances that remain largely beyond our direct perception. Yet, it is through this very act of seeking, of questioning the apparent, that we expand the boundaries of our knowledge and deepen our appreciation for the intricate elegance of physical laws. To contemplate these invisible architects of the cosmos is to embrace a profound humility, recognizing that our understanding is always evolving, always reaching for the next horizon of discovery, even as the ultimate answers remain just beyond our current grasp. And in this contemplation, we might find a quiet sense of belonging, a recognition that our own consciousness, our capacity for wonder, is itself a part of this grand, ongoing cosmic unfolding. A brief flicker of awareness in a universe so vast and so deeply enigmatic. We are, in a very real sense, the universe becoming aware of its own hidden depths, its own silent, powerful secrets, patiently waiting to be understood by the very matter it has shaped. A silent challenge, inherent, a gentle reminder of our unending quest, unwavering, a profound cosmic treasure hunt that might govern their interactions, that permeates existence. With greater clarity, each new distant supernova acts as another precious, rather than a static vacuum energy. Minuscule, profound window into the intricate interplay between the attractive force of gravity and the pervasive, repulsive push, a symphony of hidden forces. While the Lambda CDM model with its dark components stands as our most successful framework, it is important to acknowledge that some scientists still explore profound alternatives to explain these cosmic phenomena. What if our current understanding of gravity itself is incomplete on the grandest scales? This is the core question behind theories of modified gravity, such as modified Newtonian dynamics, or MUND. MUND proposes that the laws of gravity, as we understand them, might need a subtle adjustment when gravitational accelerations become extremely weak, such as in the diffuse outer regions of galaxies. Instead of unseen dark matter providing the extra gravitational pull, MUND suggests that gravity simply acts more strongly than predicted at these vast distances. While MUND has shown some success in explaining the rotation curves of individual galaxies without dark matter, it faces significant challenges in accounting for observations of galaxy clusters and the cosmic microwave background. The very existence of such alternative frameworks, even if less favored by current data, underscores the vibrant and self-correcting nature of scientific inquiry, reminding us that no theory is ever truly absolute, and the universe's secrets are always open to deeper, more nuanced interpretations. This ongoing dialogue between observation and theory, between established models and bold new ideas, is the very engine of scientific progress, a quiet, continuous dance. The intricate balance between dark matter, dark energy, and ordinary matter is not merely a matter of cosmic accounting. It is the very determinant of the universe's geometry and its ultimate fate, a cosmic tapestry woven by unseen threads. Imagine the universe as a vast, delicate sculpture, its form and destiny shaped by the unseen hands of these fundamental components. The precise cosmic inventory, refined through decades of meticulous observation, tells us that the universe is remarkably flat, meaning that two parallel lines, if extended infinitely, would never meet and never diverge. This flatness is a critical observation, suggesting a total energy density very close to a specific critical value. If the universe had significantly more matter, it would be closed, eventually collapsing back in on itself in a big crunch, a dramatic, fiery end. If it had significantly less, it would be open, expanding forever at an ever-increasing rate until everything is infinitely diluted, a gentle fade into an endless void. The observed flatness implies a near-perfect balance, a cosmic equilibrium where the repulsive push of dark energy precisely counters the attractive pull of dark matter and ordinary matter, leading to a universe that continues to expand, but whose global geometry remains elegantly uncurved. This delicate balance, a cosmic serendipity, allows for the long-term evolution and persistence of complex structures, including galaxies, stars, and ultimately, life, a fragile blossom. Indeed, the universe has not always been as it is now. Its very character has transformed over eons, driven by the changing dominance of these cosmic constituents. A scorching, hot, dense soup of radiation and particles, a primordial soup. During this radiation-dominated epoch, the energy density of photons and other relativistic particles was so immense that their outward pressure largely dictated the universe's expansion, preventing early structure formation. As the universe expanded and cooled over hundreds of thousands of years, matter began to play a more significant role. The matter-dominated epoch saw the gravitational clumping of dark matter and ordinary matter, forming the first stars and galaxies, weaving the intricate cosmic web we observe today. It was a time when gravity's gentle hand slowly pulled structures together, fostering the conditions for complexity and the birth of luminous worlds. However, roughly 5 billion years ago, a pivotal shift occurred. Dark energy, previously a subtle presence, began to assert its dominance, its pervasive influence growing stronger as space itself expanded. As the density of matter and radiation diluted, the energy density of dark energy, if it truly is the cosmological constant, remained constant or even increased relative to the other components. This ushered in the current dark energy-dominated epoch, where the universe's expansion began to accelerate, inexorably pushing galaxies apart, leading to the heat death we discussed. This sequence of cosmic epochs is a grand narrative of transformation, a story of evolving forces, each playing its part in shaping the destiny of everything that exists. A slow, majestic dance through time. Considering these colossal, invisible forces and their profound influence on the cosmic stage, naturally brings us to ponder our own place within this grand design. We exist in a universe where the visible, tangible aspects of reality are but a small fraction, where the vast majority is hidden, silent, yet undeniably powerful. This realization can evoke not a sense of insignificance, but rather a profound wonder and a deeper appreciation for the delicate balance that has allowed our existence to emerge. The precise values of dark matter and dark energy, the fine-tuning of these cosmic parameters, have allowed for the formation of galaxies, the birth of stars, the synthesis of heavy elements, and ultimately, the intricate chemistry that led to life on Earth. Had these values been slightly different, even by a small margin, the universe might have been a very different place, a rapidly expanding void, too dilute for stars to form, or a quickly collapsing cosmos, devoid of the time needed for complex structures to evolve. Our brief conscious presence in this particular cosmic epoch, where light can still travel across vast distances and galaxies are still observable, is a remarkable and fleeting consequence of these invisible forces. It is a privilege to be part of a universe that, through its own majestic and patient processes, has become aware of itself, contemplating, awaiting understanding. The journey to fully comprehend dark matter and dark energy is far from over. It represents the cutting edge of cosmological research, a frontier where the most advanced telescopes, particle detectors, and theoretical models converge in a singular quest. Future generations of observatories, such as the James Webb Space Telescope and upcoming ground-based giants like the Square Kilometre Array, will continue to map the universe with unprecedented detail, searching for new clues in the faint light from the earliest galaxies and the subtle distortions of space-time. Experiments designed to directly detect dark matter particles are becoming ever more sensitive, pushing the limits of technology to finally capture a direct interaction. A whisper from the dark. Theoretical physicists continue to explore exotic new particles and modified theories of gravity, seeking a more fundamental understanding that might unify these mysterious forces with the known laws of physics, weaving a more complete tapestry. Perhaps one day, a new, elegant theory will emerge, one that explains not only the existence of dark matter and dark energy, but also integrates them seamlessly into a grander, more complete picture of the cosmos, a harmonious truth. Until then, these invisible forces remain a profound testament to the universe's enduring capacity for mystery, a silent invitation to continue our quiet contemplation of its endless wonders and embrace the beauty of the unknown. The profound realization that 95% of our universe operates under the influence of unseen, enigmatic forces, dark matter and dark energy, does more than merely complete our cosmic inventory. It fundamentally challenges the very pillars of modern physics, inviting us to contemplate what lies beyond our current understanding. The lambda CDM model, while remarkably successful in describing the universe's evolution, is built upon two components whose fundamental nature remains elusive. This presents not a failure of science, but rather a compelling frontier, a vast expanse of the unknown that promises to reshape our most cherished theories and expand our perception of reality itself. It suggests that our current standard model of particle physics, which so elegantly describes the fundamental particles and forces governing ordinary matter, is profoundly incomplete. The Standard Model, a triumph of 20th century science, has successfully explained the behavior of quarks, leptons, and the forces that bind them, but it offers no candidate particles for dark matter and no inherent mechanism for the repulsive force of dark energy. This absence is not a minor oversight. It is a glaring omission, a silent yet insistent call for new physics. Scientists are actively exploring extensions to the Standard Model, proposing entirely new classes of particles, like WIMPs or axions for dark matter, or entirely new fields, such as quintessence, to account for dark energy. The search for these elusive entities is a delicate dance between theoretical prediction and experimental verification, a patient quest in laboratories deep underground and at the highest energy accelerators. Each non-detection, while seemingly a setback, actually helps to narrow the vast parameter space, guiding researchers closer to the hidden truths that may lie just beyond our present technological reach, or perhaps our conceptual grasp. One of the most perplexing aspects of dark energy, particularly if it is indeed the cosmological constant, is a problem known as the vacuum catastrophe, or the cosmological constant problem. According to quantum field theory, empty space, the vacuum, is not truly empty. Instead, it is a bustling arena of virtual particles constantly popping into and out of existence, contributing an enormous amount of energy to the vacuum. When physicists attempt to calculate this vacuum energy, their theoretical predictions yield a value that is an astonishing 120 orders of magnitude larger than the observed value of dark energy. This is arguably the largest discrepancy between theory and observation in the entire history of science. It is not merely a small error, it is a colossal chasm, suggesting a fundamental misunderstanding at the intersection of general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the subatomic world. Reconciling this profound puzzle could lead to a revolutionary new physics, a grander theory that seamlessly integrates these two seemingly disparate domains, providing a unified understanding of reality. The resolution of the dark matter and dark energy mysteries could therefore hold the key to unlocking some of the deepest secrets of the universe, potentially leading to a grander unification of fundamental forces. Imagine a future where we understand how gravity, currently described by general relativity, seamlessly merges with the quantum realm, where the elusive dark matter particles are revealed to be integral components of a more complete particle physics model, and where dark energy is understood not as an arbitrary constant, but as a natural emergent property of space-time itself, perhaps tied to the very quantum foam of the vacuum. Such a unified theory would not only explain the 95% of the universe we currently cannot see, but it would also provide a coherent framework for understanding the universe from its smallest quantum fluctuations to its largest cosmic structures, from the birth of time to its ultimate, serene end. This vision inspires generations of physicists, driving them to probe deeper, to ask bolder questions, and to seek the elegant simplicity that often underlies the universe's most complex phenomena. Furthermore, the precise value of dark energy, this cosmic constant that dictates the universe's expansion, has prompted deep philosophical and scientific reflections, including connections to the intriguing concept of the multiverse. If the cosmological constant is indeed a fundamental property of space, its observed value appears remarkably just right to allow for the formation of complex structures and ultimately, life. If it were significantly larger, the universe would have expanded too rapidly for galaxies to form. If it were much smaller, or even negative, the universe would have collapsed before life could emerge. This apparent fine-tuning has led some theorists to consider the idea that our universe might be just one of an infinite ensemble of universes, a multiverse, each with slightly different physical laws and constants. In this scenario, we simply find ourselves in one of the universes where the conditions are conducive to life, making the fine-tuning a statistical inevitability rather than a cosmic coincidence. This perspective, while still highly speculative, offers a different lens through which to view our unique existence, suggesting that our particular slice of reality is but one of countless possibilities. A single, delicate bubble in an infinitely grander cosmic foam. Ultimately, the persistent enigmas of dark matter and dark energy serve as a profound reminder of the boundless depths of the universe's mysteries and the enduring power of human curiosity. As we drift into the quiet contemplation of these unseen forces, we are invited to embrace the intellectual humility that comes with acknowledging the vastness of the unknown. Our quest to understand these cosmic constituents is not just about filling in the blanks of our equations. It is about expanding our very consciousness, challenging our anthropocentric views, and connecting us more deeply to the grand unfolding narrative of the cosmos. To realize that we are part of a universe so profoundly shaped by forces we cannot directly perceive, yet can infer through their majestic gravitational whispers and expansive pushes, is to experience a unique sense of wonder. It reminds us that our search for knowledge is an ongoing, infinite journey, and that even in the quiet of the night, the universe continues to reveal its secrets, patiently awaiting our ever-deepening understanding. A silent, profound invitation to dream on. The universe, in its majestic unfolding, continues to present us with its deepest enigmas, and the twin mysteries of dark matter and dark energy represent the most compelling frontiers of modern cosmology. We stand at a pivotal moment, equipped with an ever-growing arsenal of observational tools and theoretical frameworks, eager to peel back the layers of cosmic darkness. The quest is not merely to confirm the existence of these invisible forces, for their gravitational and expansive influences are already undeniable. Rather, it is to understand their fundamental nature, to discover what they truly are and how they fit into the grand tapestry of physical laws. This pursuit promises not just new answers, but potentially a profound reorientation of our understanding of reality itself, a quiet revolution in thought that builds upon the foundations laid by giants before us, yet extends far beyond their initial imaginings. For dark matter, the experimental search is a patient and arduous endeavor, demanding the utmost precision and ingenuity. Scientists around the globe are employing a diverse array of strategies to detect these elusive particles, which are believed to interact only incredibly weakly with ordinary matter. Direct detection experiments, housed in laboratories deep beneath mountains to shield them from interfering cosmic radiation, utilize vast detectors filled with supercooled noble liquids like xenon or germanium crystals. The hope is that a dark matter particle, silently streaming through the Earth, might occasionally collide with an atomic nucleus within these detectors, producing a tiny, measurable recoil. Projects such as Xenon-T in Italy and Lux Zeppelin in the United States are at the forefront of this effort, constantly pushing the sensitivity limits, waiting for that single, definitive whisper from the dark. Meanwhile, indirect detection experiments look for the annihilation products of dark matter particles in regions where they are thought to be abundant, such as the galactic center or dwarf galaxies. Telescopes sensitive to gamma rays, X-rays, and neutrinos search for characteristic energy signatures that would betray the presence of dark matter annihilation or decay. Finally, particle accelerators like the Large Hadron Collider at CERN offer a different avenue, attempting to create dark matter particles in high-energy collisions, much as other fundamental particles have been discovered, by observing missing energy or momentum that indicates the production of unseen particles. Each of these approaches, though challenging, systematically narrows the possibilities, slowly illuminating the path forward. The quest to comprehend dark energy, on the other hand, relies less on direct detection and more on meticulous observation of the universe's large-scale structure and expansion history. Future generations of astronomical surveys are designed to map billions of galaxies across vast cosmic distances with unprecedented accuracy, providing a clearer picture of how dark energy has influenced the universe's growth over billions of years. Missions like the European Space Agency's Euclid Telescope, the Nancy Grace Roman Space Telescope from NASA, and the ground-based Vera C. Rubin Observatory's Legacy Survey of Space and Time are poised to deliver truly colossal data sets. By observing the distribution of galaxies, the patterns of gravitational lensing, and the precise distances and recession velocities of distant supernovae, these instruments will refine our measurements of the dark energy's equation of state parameter. This parameter is crucial as it tells us whether dark energy is a true cosmological constant, an intrinsic property of space, or a more dynamic, evolving field like quintessence. Furthermore, new experiments designed to study the cosmic microwave background with even greater sensitivity, such as CMB-S4, will provide invaluable insights into the very early universe, potentially revealing subtle signatures of dark energy's influence in its primordial state. These cosmological probes are like archaeologists of the cosmos, carefully excavating the universe's past to understand its present and predict its serene, distant future. The potential implications of a definitive discovery regarding dark matter or dark energy are truly transformative, promising a paradigm shift in our understanding of fundamental physics. If dark matter particles are finally detected, it would necessitate an extension of the Standard Model, introducing new particles and potentially new fundamental forces. This could open doors to a richer, more complete picture of the subatomic world, revealing symmetries and interactions currently unimagined. Similarly, if the precise nature of dark energy is uncovered, whether it confirms the cosmological constant or points to a dynamic field, it would profoundly impact our theories of gravity and the very structure of space-time. It might even provide crucial clues for a grand unified theory, one that seamlessly weaves together general relativity with quantum mechanics, resolving the perplexing vacuum catastrophe and offering a coherent description of the universe from its smallest quantum jitters to its largest cosmic stretches. Such a breakthrough would not just be a scientific achievement, it would be a profound intellectual awakening, inviting us to see the universe through entirely new eyes, with a deeper appreciation for its hidden, intricate workings. This journey into the dark side of the universe, this patient unraveling of its most profound secrets, is more than just an academic pursuit. It is a fundamental human endeavor, a reflection of our innate drive to comprehend the cosmos of which we are an integral part. To realize that the vast majority of existence remains unseen, yet powerfully shapes our reality, can evoke a unique sense of humility and wonder. It is a reminder that the universe is far more complex and subtle than our immediate perceptions suggest. A grand and elegant design that continues to surprise us with its hidden depths. As we continue to gaze at the tranquil night sky, knowing that most of what truly governs its majesty remains a profound mystery, we are invited to embrace the beauty of this unknown. Our consciousness, our capacity for inquiry, is itself a product of these cosmic forces, a brief yet brilliant flicker of awareness in a universe that is slowly, patiently revealing itself. May these deep reflections on the invisible forces governing the universe carry you into a world of tranquil sleep, a peaceful contemplation of a reality far richer and more mysterious than we could ever fully grasp, yet one we continue to explore with endless curiosity, precise balance between dark matter and dark energy, and their comparable densities in the present epoch, also presents a profound cosmological puzzle known as the cosmic coincidence problem. For billions of years after the Big Bang, matter, both ordinary and dark, dominated the universe, its gravitational pull slowing the expansion. Dark energy, if it is a cosmological constant, remained constant in density, while matter density decreased as the universe expanded and diluted. It was only relatively recently, in the last few billion years of the universe's 13.8 billion-year history, that dark energy's influence began to significantly surpass that of matter, leading to the observed acceleration. The coincidence lies in why these two vastly different components with such different evolutionary paths happen to have comparable energy densities right now, at precisely the epoch when intelligent life capable of observing them has emerged. This is not a trivial question. It feels like an extraordinary stroke of cosmic luck, almost as if the universe were designed for our specific moment of observation. This apparent fine-tuning has led to much contemplation, with some scientists exploring the anthropic principle as a potential, albeit controversial, explanation. The anthropic principle suggests that the fundamental constants and properties of the universe must be precisely as they are, because if they were significantly different, we would not exist to observe them. In the context of the cosmic coincidence, it posits that perhaps only in universes where dark energy and matter densities are comparable at a certain stage can galaxies and stars form over long enough timescales for complex chemistry, and ultimately, life to evolve. If dark energy had become dominant much earlier, the universe would have expanded too quickly, preventing matter from clumping into galaxies. If it had become dominant much later, gravity might have already caused the universe to recollapse. Our existence, therefore, might be intimately linked to this delicate balance, suggesting that our observable universe is but one of many, a member of a vast multiverse where only those universes with just right conditions allow for observers like us to arise. This perspective gently shifts the focus from a single, coincidental universe to a landscape of possibilities, a cosmic lottery where our particular existence is a winning ticket in a grand, silent draw. Yet, many physicists find the anthropic principle unsatisfying, preferring a more fundamental explanation rooted in the underlying laws of physics. They seek a deeper theory that would naturally predict the observed values of dark matter and dark energy, resolving the cosmic coincidence without resorting to statistical arguments from a multiverse. Such a theory might reveal a hidden symmetry or a new fundamental interaction that governs the behavior of these dark components, linking them inextricably to the known forces of nature. Perhaps dark energy is not a simple constant, but a dynamic field whose evolution is determined by a deeper physical principle, leading it to become dominant precisely when it does. The pursuit of this more elegant and predictive explanation continues to drive theoretical research, pushing the boundaries of our mathematical and conceptual tools. It is a quest for a profound simplicity hidden beneath the apparent complexity, a harmonious truth that would unify the disparate elements of our cosmic understanding into a single, elegant narrative. The implications of these invisible forces extend beyond the purely physical, touching upon our understanding of space, time, and consciousness itself. To know that the universe's expansion is not merely a passive coasting, but an active acceleration driven by a mysterious energy inherent to space, subtly alters our perception of the void. Empty space is not nothing. It is a dynamic, energetic entity, constantly creating more of itself, pushing everything apart. This ongoing creation, this relentless stretching, is the ultimate backdrop against which our lives unfold. Our sense of scale, our perception of duration, even our very concept of now, are shaped by this cosmic dance of the visible and the invisible. The dark universe invites us to transcend our immediate sensory experience, to connect with the subtle, pervasive forces that orchestrate the grand cosmic ballet, reminding us that we are woven into a reality far grander and more mysterious than we often dare to imagine. It is a quiet invitation to reflect on the deep interconnectedness of all things, from the smallest quantum fluctuation to the largest cosmic structure, all part of this magnificent, silent unfolding. As we consider the future of this profound scientific quest, it is clear that the journey to fully unravel dark matter and dark energy is a marathon, not a sprint, a patient and collective human endeavor. The next generation of cosmic observatories and experiments will continue to refine our measurements, seeking out anomalies that might point to new physics. The European Space Agency's Euclid mission, launched recently, is specifically designed to create a three-dimensional map of the universe by observing billions of galaxies over the past 10 billion years, meticulously charting the evolution of cosmic structure and the expansion rate. This will provide unprecedented precision in measuring dark energy's properties, allowing scientists to discern whether it is indeed a constant cosmological constant or if its strength varies over time. Such subtle changes would have profound implications, potentially ruling out the simplest models and opening new theoretical avenues, guiding us closer to the heart of this cosmic engine. Simultaneously, the search for dark matter particles will intensify, with new experiments employing even more sophisticated detectors and innovative techniques. The search for WIMPs continues, but researchers are also broadening their scope, investigating other hypothetical particles, like axions, which might be extremely light and interact even more feebly than WIMPs. These experiments often leverage the quietest places on Earth, abandoned mines and deep ice sheets, to minimize background noise, creating pristine environments where a faint signal from a dark matter particle might finally be unambiguously detected. The synergy between these ground-based particle physics experiments and astronomical observations is crucial. Each piece of evidence, whether a direct detection or a refined cosmological measurement, acts as a constraint, helping to build a more coherent and complete picture of these invisible components, much like slowly assembling a vast, intricate puzzle with pieces drawn from across the cosmos. Beyond these experimental frontiers, theoretical physicists continue their tireless work, developing new models and mathematical frameworks that aim to unify our understanding of these dark components with the known laws of physics. Concepts like string theory, with its proposal of extra spatial dimensions and vibrating fundamental strings, or theories of quantum gravity, which seek to merge general relativity with quantum mechanics, may eventually offer a more fundamental explanation for the existence and properties of dark matter and dark energy. The vacuum catastrophe remains a powerful motivator, pushing theorists to seek an underlying principle that naturally yields the observed, incredibly small value of the cosmological constant, rather than the vastly larger prediction from quantum field theory. This intellectual pursuit is a testament to the human spirit's unwavering desire to understand the deepest truths of existence, to find an elegant simplicity amidst the universe's profound complexities, a silent, continuous whisper of inquiry that echoes through the vastness of space and time. The intricate, profound mysteries of dark matter and dark energy, while challenging our deepest scientific assumptions, simultaneously illuminate the very process of scientific discovery itself. They remind us that the boundaries of knowledge are not fixed, but fluid, constantly receding as we push further into the unknown with our instruments and our minds. This journey into the cosmic darkness is, at its heart, a testament to humanity's insatiable curiosity. Our enduring drive to understand the universe not just in its visible, shimmering grandeur, but also in its hidden, silent depths. It is a meticulous process of asking fundamental, often uncomfortable questions, gathering increasingly precise data with our most advanced observatories, and constructing ever more refined theoretical frameworks. This is a journey that often reveals how much more there is to learn, rather than providing definitive answers. The very existence of these elusive components compels us to refine our observational tools, expand our theoretical imagination, and embrace the humbling realization that our current, human-centric understanding of reality is merely a temporary stepping stone on an infinitely longer path toward a more complete cosmic awareness. This patient, methodical unraveling of the universe's most profound secrets is a quiet, continuous act of intellectual courage, pushing the very limits of our collective comprehension. One of the most radical and perhaps disquieting implications of dark energy, particularly if it truly is the cosmological constant, the inherent energy of the vacuum, is its profound effect on our intuitive understanding of nothingness. For much of human history, and indeed for a significant portion of scientific history, the vacuum of space was conceived as precisely that: an empty void, a passive arena devoid of substance or activity, a blank canvas. However, quantum mechanics, with its vibrant tapestry of virtual particles constantly flickering into and out of existence, has already shown us that the vacuum is far from inert. It is a seething, energetic quantum foam, a restless sea of fleeting possibilities. Dark energy takes this concept further, suggesting that this inherent quantum energy of space is not just a theoretical curiosity or an abstract calculation, but a tangible, pervasive, and repulsive force that actively drives the universe apart. It is as if the very fabric of space-time is not a passive stage upon which cosmic events unfold, but an active, dynamic participant in the grand cosmic drama, a restless ocean imbued with a subtle, yet undeniable outward pressure that shapes all large-scale structures. This radical redefinition of nothingness, transforming it from a mere absence into a dynamic, energetic entity, forces us to confront the deepest philosophical implications of quantum field theory and its perplexing, almost irreconcilable, relationship with general relativity. To reconcile the observed, incredibly tiny value of dark energy with the enormous, almost absurd predictions of quantum mechanics remains one of the most pressing and profound challenges in theoretical physics, a silent chasm bridging two fundamental pillars of our understanding, patiently awaiting a revolutionary insight that could redefine our very concept of existence. The pursuit of dark matter and dark energy, therefore, stands as a beacon for the potential unification of physics, a grand scientific aspiration that has captivated thinkers for centuries. The Standard Model of particle physics, while a remarkable success in describing three of the four fundamental forces, the strong, weak, and electromagnetic interactions, does not encompass gravity, nor does it provide any candidate particles for these dark components. This is not a slight imperfection, but a profound lacuna, an undeniable indicator that our current model is incomplete, like a magnificent symphony missing its deepest bass notes and highest ethereal melodies. A truly unified theory, often referred to as a theory of everything or a quantum theory of gravity, would ideally integrate gravity with quantum mechanics and naturally account, explaining their observed abundances and behaviors with elegant precision. Such a grand synthesis would represent the pinnacle of human intellectual achievement, providing a single, coherent framework for understanding all the fundamental constituents and interactions of the universe. It would bridge the vast conceptual divide between the microscopic realm of quantum particles, with their probabilistic uncertainties and strange entanglements, and the macroscopic expanse of cosmic structures, governed by the elegant curves of space-time, offering a profound sense of intellectual closure, a harmonious resonance in the symphony of reality. The journey toward this ultimate unification is long and arduous, fraught with conceptual difficulties and experimental challenges that will demand the brightest minds of generations to come. Yet, the tantalizing promise of such a comprehensive understanding continues to inspire physicists, guiding their inquiries into the deepest recesses of existence. A quiet, persistent yearning for cosmic truth that transcends individual lives and spans millennia, weaving its way through every thought and observation. These invisible forces also offer a unique and deeply contemplative lens through which to ponder our own fleeting existence within the grand cosmic narrative. We, as conscious beings capable of abstract thought and profound inquiry, are privileged witnesses to a universe that is still in its relatively early, dynamic stages, a brief, vibrant moment before the onset of its ultimate, serene heat death. The light from distant galaxies, stretched and dimmed by the accelerating expansion of space, still reaches us, allowing us to glimpse the universe's primordial past and infer its far-flung future. This capacity for observation, for reflection, for wonder, is itself a remarkable and delicate product of the intricate interplay between dark matter's gravitational embrace, which allowed structures to form, and dark energy's expansive push, which set the stage for long-term evolution. Had these forces been slightly different, even by minuscule amounts, a fraction of a percentage point, the universe might never have formed the stars and planets necessary for the synthesis of heavy elements, or it might have expanded too quickly for complex chemistry to emerge, or collapsed too soon for life to take hold. Our very awareness is therefore intimately woven into the fabric of these cosmic mysteries, a fragile, luminous pattern within an overwhelmingly dark and enigmatic cosmos. This profound connection invites us to find beauty not just in what we know, but in the vast, elegant unknown that surrounds us, inspiring a deep sense of belonging within the universal dance of matter and energy. A quiet harmony echoing through the stillness. As we conclude this contemplation of the invisible forces that govern the universe, let us carry with us a profound sense of awe and intellectual satisfaction. The ongoing quest to understand dark matter and dark energy is a testament to the enduring human spirit, our relentless pursuit of knowledge, and our boundless capacity for wonder in the face of the unknown. It reminds us that the universe is not a static stage, but a dynamic, evolving entity, constantly revealing new layers of complexity and beauty. The silent, pervasive influence of these dark components shapes not only the cosmic landscape, but also our very perception of reality, inviting us to dream of a future where these mysteries are finally unveiled, integrated into a grander, more complete understanding of everything. Until then, let the quiet grandeur of the dark universe be a source of calm inspiration, a gentle guide into the realms of restful thought and peaceful slumber, knowing that even in the deepest silence, the cosmos continues its magnificent hidden work, and we are part of its conscious awakening. This realization that our existence is intertwined with forces both seen and unseen allows for a tranquil acceptance of the vastness, a peaceful surrender to the endless unfolding cosmic story. As we gently drift through the final moments of our exploration into dark matter and dark energy, we are left with a profound sense of the universe's enduring capacity for mystery. We have peered into the invisible scaffolding that holds galaxies together and contemplated the accelerating push that dictates the cosmos's ultimate fate. These unseen forces, which orchestrate 95% of all existence, stand as silent, magnificent monuments to the vastness of what we still do not comprehend. Yet it is precisely in this recognition of the unknown that we find a deeper appreciation for the beauty and elegance of the physical laws that govern our reality, and for the tireless human spirit that seeks to understand them. Our journey through these cosmic enigmas, fully revealed canvas, but an ever-unfolding narrative, rich with secrets waiting to be discovered. The silent dance of dark matter and the pervasive whisper of dark energy are not distant, abstract concepts, but fundamental components woven into the very fabric of our being, shaping the stars above and the atoms within us. This ongoing quest for knowledge, this patient unraveling of the cosmos's deepest truths, is a testament to our collective curiosity, connecting us to a story that began billions of years ago and will continue long after our brief, conscious flicker. It is a peaceful realization that we are not separate from this grandeur, but rather an intricate, aware part of its majestic, silent unfolding. May these deep thoughts about dark matter and dark energy. Remember that the universe is amazing, and you are a part of it. Fall asleep with this feeling of serenity and endless knowledge. Good night.